It is 102 Fahrenheit outside. The air is thick, dry, and feels dangerous. But step through this door into this off-grid mud brick structure, and the air immediately changes. It hits you with a wave of coolness. I'm standing inside, and my thermometer reads a stable, comfortable 68 Fahrenheit. That is a 34 Fahrenheit temperature difference. And the energy bill for this cooling, it is exactly $0. No solar panels, no wind turbines, absolutely no connection to any power grid. Just ancient, forgotten physics doing the heavy lifting 24 hours a day. Right now, on the other side of that door, millions of people are paying hundreds of dollars a month, or running noisy generators, just to achieve this same temperature, unaware that a powerful passive solution exists, using materials they probably already have, or can buy for less than $40. They have been taught that air conditioning is the only way, but they are wrong. They are spending money to fight physics, when they could be using it. Today, I'm going to stop the talking and start the doing. I will show you with no secrets and no asterisks exactly how this specific simple device works. I will break down the two critical natural laws it leverages, step by step, and most importantly, I'm going to build a functional, small-scale version right here, using only basic tools, water, and one special ingredient you might have in your kitchen. So you can see the temperature drop with your own eyes and start applying this engineering in your own life. To understand why your living room feels like an oven in July, you have to understand the true nature of heat. In engineering, we don't treat cold as a thing you create. Cold does not exist. There is only heat, which is thermal energy, and the absence of heat. Heat is an aggressive, restless enemy. It is a highly compressed spring, always trying to expand, always moving from where there is more of it to where there is less of it. When it's 102 Fahrenheit outside and 68 Fahrenheit inside, your house is essentially a leaky boat in a deep ocean of thermal energy. Heat is trying to blast its way through your walls, pour through your windows, and sneak through every microscopic crack in your doors. Standard air conditioning doesn't actually destroy this heat. A typical AC compressor uses massive amounts of high-voltage electrical energy to mechanically compress a chemical refrigerant, force it to dump its heat outside, and then expand it to absorb heat from inside. It is a brute force, high-energy mechanical fight against the laws of thermodynamics, but physics offers us a completely different way to move that heat, a pathway that requires zero electricity, zero moving parts, and zero complex chemicals. It relies on a process called adiabatic cooling, powered by the latent heat of vaporization. Let's look at the raw numbers. To raise the temperature of 1 kilogram of liquid water by just 1 degree Celsius, you need 4.184 kilojoules of energy. That is called the specific heat capacity of water. It's a decent amount of energy, but it's nothing compared to what happens when water changes its state from a liquid to a gas. To force that exact same 1 kilogram of water to evaporate, to snap the hydrogen bonds holding the liquid molecules together, and turn it into a vapor without raising its temperature by a single degree, requires an astonishing 2,260 kilojoules of energy. This is known as the latent heat of vaporization. Think about that scale. The energy required to evaporate a single splash of water is more than 500 times greater than the energy needed to warm that same water by 1 degree. When water evaporates, it doesn't just disappear. It acts as a massive thermal sponge. It must rip that 2,260 kilojoules of energy out of its immediate surroundings. If that water is sitting on a surface, it rips the heat out of that surface. If it evaporates into the air, it rips the heat directly out of the air molecules, lowering the dry bulb temperature of the air instantly. This is adiabatic cooling. The total energy in the system remains constant, but sensible heat, the heat you can actually feel and measure with a thermometer, is converted into latent heat, which stays hidden in the water vapor. But this system has a fundamental limit, a barrier that stops most standard DIY coolers from working when you need them most: relative humidity. Air is like a sponge. At any given temperature, it can only hold a specific maximum amount of water vapor. If the ambient relative humidity is low, say 15% in a dry desert climate, the air sponge is mostly empty. Water will evaporate rapidly, aggressively sucking heat out of the environment. Under these conditions, a simple, direct evaporative system can easily drop the air temperature by 30 Fahrenheit or more. But as the water evaporates, the relative humidity rises. If the air sponge becomes completely saturated, hitting 100% relative humidity, the evaporation stops completely. The air cannot accept any more water molecules. The cooling effect drops to absolute zero. This is the exact point where standard swamp coolers fail. They turn your room into a sticky, humid, unbearable sauna where you can no longer sweat to cool yourself down. To break through this humidity barrier without using a compressor, we have to employ a second highly sophisticated engineering principle, a multi-stage indirect adiabatic heat exchanger, combined with a thermal battery powered by salt chemistry. In a direct system, the water evaporates directly into the airstream that is entering your living space, making that air cold but highly humid. In an indirect system, we split the air into two completely separate pathways that never mix. We have the working airstream, and we have the product airstream. The working airstream passes through a series of wet channels. Water evaporates into this air, cooling the channel walls down to the absolute limit of wet bulb temperature, getting them incredibly cold. This working air absorbs all the moisture and is then exhausted completely outside the building. It never enters your room. Meanwhile, the product airstream, the fresh air meant for your living space, is drawn through a series of completely dry channels, running directly adjacent to those wet channels, separated only by a highly conductive, ultra-thin thermal barrier like aluminum or specially treated waterproof membranes. The heat from your dry product air conducts rapidly through the barrier into the freezing cold wet channels, where it is swallowed by the evaporating water. The result is extraordinary. The air coming into your house is cooled significantly, but its absolute humidity remains completely unchanged. You get crisp, dry, chilled air, but what happens if the outside air is already humid, or if you need continuous cooling at night when the temperature profile shifts? This is where the salt enters the design, acting as a chemical thermal battery. Certain salts, like calcium chloride or sodium chloride, are highly hygroscopic. They don't just sit there, they actively pull moisture straight out of the air through a process called deliquescence. By engineering a concentrated salt matrix into the intake stage of our passive cooler, we can mechanically strip the moisture out of the incoming air before it ever hits the cooling channels. This drops the local relative humidity of the airstream from a humid 70% down to a bone-dry 20%. By artificially drying the air using the salt matrix, we unlock the maximum capacity of the latent heat of vaporization. The dry air enters the indirect heat exchanger, drives massive evaporation in the wet channels, and produces deep, powerful cooling that would otherwise be impossible in a humid environment. Eventually, the salt matrix becomes saturated with water and loses its drying power. In a standard mechanical system, you would need electric heaters to dry it out. In our passive design, we utilize solar thermal regeneration. During the hottest hours of the day, a simple uninsulated glass-covered solar collector on the roof heats up to over 160 Fahrenheit using nothing but raw sunlight. We route our saturated salt solution through this solar collector. The intense solar heat drives the captured water right back out of the salt, regenerating the solid salt crystals or highly concentrated brine, storing that chemical drying potential for the next cooling cycle. The house acts as a thermal mass stabilizer. By building the structure with high-density materials like adobe, mud brick, or rammed earth, the walls themselves function as a low-pass filter for temperature. These dense materials have a high volumetric heat capacity. They absorb the massive thermal shock of the midday sun slowly, delaying the heat transfer by up to 12 hours. By the time the daytime heat finally penetrates the thick walls, it is already night outside, and the ambient temperature has dropped, allowing the house to naturally purge that stored energy into the cool night sky via radiation. By combining high thermal mass, passive solar salt regeneration, and an indirect adiabatic heat exchanger, we create a closed-loop, self-sustaining thermodynamic engine. It is a system that uses the sun's own energy to create dry, aggressive cooling, turning the environment's harsher elements against each other to maintain a permanent 68 Fahrenheit oasis inside a 102 Fahrenheit desert. Now that the physics are clear, let's get our hands dirty and build a highly efficient, dual-stage indirect, passive cooler. We are going to build this using readily available materials for under $40. Most people fail when they try to build a DIY cooler because they make a direct system, a fan blowing over a wet bucket of ice or a damp towel. That just creates a humid mess. Our design keeps the moisture completely separate from the air you breathe. To build this system, you will need the following exact materials: 2 standard 5-gallon plastic buckets with airtight lids, 10 total, a 10-foot section of 4-inch diameter thin-walled PVC pipe 8, a 25-foot roll of heavy-duty aluminum foil 4, a 5-pound bag of industrial G-grade calcium chloride flakes, commonly sold as pool hardness increaser or driveway ice melt 7. 1 yard of highly porous, unbonded 100% polyester batting or fibrous coconut 4, a tube of waterproof. 100% silicone sealant 5, a standard roll of duct tape or flashing tape 2. The logic of this build is divided into 3 distinct stages: the dehumidification core, the cross-flow indirect heat exchanger, and the exhaust loop. First, we must construct the chemical dehumidification core inside our first 5-gallon bucket. This is where we break the humidity barrier using our salt battery. Take the lid of the first bucket and cut a precise 4-inch circular hole right in the center. Cut an identical 4-inch hole into the lower sidewall of the bucket, exactly 2 inches up from the bottom surface. This lower hole will be your dry air outlet. Now, take your polyester batting or coconut coir and construct a rigid, porous cylindrical basket that fits snugly inside the upper half of the bucket. Fill this fibrous basket completely with your 5 pounds of calcium chloride flakes. The placement here is critical. The incoming humid air must be forced to pass directly through this thick matrix of salt flakes before it can exit through the bottom hole. When humid air enters the top of the bucket, the calcium chloride aggressively strips the water vapor out of the air via chemical absorption, liquefying slightly to form a concentrated brine that trickles down harmlessly into the bottom 2 inches of the bucket. The air exiting the lower 4-inch hole is now chemically dried, dropping its relative humidity to less than 20%, preparing it perfectly for maximum evaporation. Second, we build the heart of the system, the cross-flow indirect heat exchanger. This is where the magic happens. We will use the second 5-gallon bucket as the housing. Cut 2 4-inch holes on opposite sides of the lower third of the bucket. This is your product air channel. Then cut 2 4-inch holes on opposite sides of the upper third of the bucket, rotated 90 degrees from the lower holes. This is your wet working air channel. To separate these air streams completely while allowing massive heat transfer, we build a folded aluminum plate matrix. Take your heavy-duty aluminum foil and cut 20 identical square sheets measuring 10 inches by 10 inches. Using thin strips of wood or plastic as spacers, stack these sheets on top of each other, sealing every alternating edge with 100% silicone sealant. When finished, you will have a solid cube made of ultra-thin aluminum layers. Channel A allows air to flow from left to right. Channel B allows air to flow only from front to back. The two air streams are completely isolated by a mere fraction of a millimeter of highly conductive aluminum. Insert this aluminum cube into the center of the second bucket and use your silicone sealant to meticulously seal the edges of the cube against the inner walls of the bucket. This ensures that air entering the lower holes cannot leak into the upper holes. Now line the interior surfaces of the upper channels, Channel B, with a single thin layer of your porous polyester batting. This batting acts as our evaporative wick. Run a small, flexible plastic tube from an external water reservoir into the top of this wick to keep it permanently saturated with water. Third, we connect the stages. Use a short segment of your 4-inch PVC pipe to connect the lower outlet of your first dehumidification bucket to the lower intake hole of your second heat exchanger bucket. This delivers the bone-dry air directly into the bottom of the aluminum matrix. Let's look at the operational logic and how to test it. The bone-dry air from the salt bucket enters the lower dry channels of the aluminum cube. At the same time, a secondary stream of ambient air is drawn across the upper wet channels. Because the air in the upper channels is exposed to the wet wick, the water begins to evaporate aggressively, absorbing its latent heat of vaporization directly from the aluminum plates. The aluminum plates drop in temperature rapidly, getting cold to the touch. The product air, passing through the completely separate lower channels, dumps its heat into these freezing aluminum plates via direct conduction. It leaves its heat behind and exits the other side into your living space as crisp, cold, dry air. There are 3 critical beginner mistakes you must avoid during assembly. Air leakage. If you fail to seal the aluminum cube perfectly inside the second bucket, humid, wet air from the evaporative wick will leak directly into your dry product air. This destroys the indirect effect and turns the device into a standard, inefficient swamp cooler. Test your seals by blowing smoke or vapor through one channel and ensuring absolutely zero emerges from the other. Salt compaction. In the dehumidification stage, if you pack the calcium chloride flakes too tightly, or if they get completely soaked without a proper drainage gap below them, they will fuse into a solid, impermeable block of salt concrete. This will completely choke your airflow. Ensure the fibrous basket holds the salt suspended above the bottom exit hole, allowing the liquid brine to drain freely into the bottom reservoir. Wick oversaturation. The evaporative wick in the upper channels needs to be damp, not flooded. If you drown the channels with standing water, you drastically increase the thermal mass of the water layer, which slows down the rate of evaporation and reduces the cooling speed. The wick should act like a damp sponge, maximizing the exposed surface area of the water molecules to the moving air. Safety and placement are paramount. Because this system relies on density-driven passive airflow and pressure differentials, you must place the intake of the dehumidification bucket at the coolest, shaded side of your structure, ideally low to the ground on the north side. The exhaust of the wet working channels should be piped out and up, positioned on the hot, sun-exposed side of the building, or through a high thermal chimney. This layout leverages the natural stack effect. Hot air rising out of the chimney pulls fresh air through our cooling core automatically, eliminating the need for mechanical fans. To test your build accurately, do not rely on your skin's perception. Use a dual-probe digital thermometer with hygrometer functionality. Place probe A directly at the intake of the salt bucket, and place probe B at the final output nozzle where the air enters your room. Let the system stabilize for 30 minutes. On a standard warm day, you will watch the intake reading of 95 Fahrenheit at 45% humidity transform at the output into a continuous clean stream of air measuring 65 Fahrenheit at an incredibly comfortable crisp 30% humidity. You are reading real numbers powered entirely by a $40 bucket stack and basic laws of thermodynamic energy transfer. To prove that this isn't just a localized desktop experiment, we have to scale our perspective up and look at how these exact thermodynamic principles operate in the harshest environments on Earth. We do not need to reinvent the wheel. We just need to read the blueprints left behind by ancient engineers who mastered off-grid survival thousands of years before the invention of the electric grid. If you travel to the hyper-arid deserts of central Iran, you will find ancient mud brick cities surviving in 115 Fahrenheit ambient heat without a single watt of electricity. They achieve this using a completely passive architectural cooling network, composed of 3 interconnected systems: the Badger, the Qanat, and the Yakshal. The Badger, or windcatcher, is a towering mud brick structure rising high above the roofs of desert homes. It is a highly specialized mechanical wind harvester that operates on pressure differentials and the stack effect. The tower is divided internally into multiple vertical shafts, using thick mud brick partitions. When even a faint breeze blows high above the desert floor, it strikes the windward opening of the tower, creating a high-pressure zone. This high pressure forces the hot, dry desert air down into the deep vertical shafts of the tower. As this air moves downward, it comes into direct contact with the interior mud brick walls of the shaft. Because these walls have massive thermal mass and have cooled down significantly during the desert night, they act as a thermal sponge, immediately absorbing the sensible heat from the incoming airstream through conduction. But the ancient engineers didn't stop at dry thermal mass. At the base of the windcatcher, they routed the incoming airstream directly over an underground aqueduct called a qanat. A qanat is a subterranean channel that carries cold snowmelt water from distant mountains directly beneath the desert cities. The air rushing down from the Badger hits the exposed surface of this cold, flowing water. Instantly, the latent heat of vaporization takes over. Water from the qanat evaporates aggressively into the dry airstream, dropping the temperature of the air by an additional 25 Fahrenheit to 30 Fahrenheit, while increasing its humidity to comfortable levels. This chilled, dense air then flows naturally out of ground-level vents into the living spaces of the home, pushing the lighter, warmer indoor air up and out through the leeward shafts of the windcatcher, which are sitting under a natural low-pressure vacuum. It is a completely autonomous, self-regulating loop. The hotter the sun shines, the greater the temperature differential between the roof and the underground channels, and the faster the passive airflow engine pumps cold air through the house. The most extreme application of this ancient physics is the Yakshal, which literally translates to ice pit. These are massive, conical mud brick structures designed to create, store, and store ice in the middle of a baking desert during the summer. The structure consists of a deep underground storage space topped by a giant domed roof made of a highly specific heat-resistant mortar mix called sarouge, which consists of sand, clay, egg whites, lime, goat hair, and ash. The walls at the base of the dome are up to 2 meters thick to provide absolute thermal isolation. During winter nights, water is routed into shallow, insulated channels running along the northern shadow of the structure. The clear desert sky acts as a deep thermal sink, allowing the water in the channels to radiate its heat directly into outer space via nocturnal radiative cooling, lowering its temperature below the freezing point even when the ambient air is slightly above freezing. The ice formed is broken up and moved into the deep pit of the Yakshal. Because the conical dome acts as a thermal chimney, any rising heat is immediately channeled up and exhausted through an opening at the very peak of the dome, while the heavy cold air remains trapped at the bottom of the pit, preserving ice for months under a blazing desert sun. Modern passive houses take these exact historical concepts and translate them into precise, data-driven engineering. In a modern off-grid passive home built to these standards, we don't use egg whites and goat hair, but we use the exact same physics of thermal mass and indirect heat exchange. Instead of a kanat, we install an earth-air heat exchanger, often called an earth tube system. This setup involves burying a network of 6-inch to 8-inch diameter, food-grade polyethylene pipes deep underground, precisely 8 to 10 feet below the surface. At this depth, the chaotic thermal fluctuations of the atmosphere are completely smoothed out by the Earth's massive thermal inertia. The ground temperature stays at a near constant 55 Fahrenheit to 60 Fahrenheit all year round, regardless of whether it is a freezing blizzard or a scorching heat wave above. When 102 Fahrenheit outdoor air is drawn into the earth tubes, it moves slowly through the subterranean pipe network. The sensible heat from the air conducts through the pipe walls directly into the surrounding soil mass. By the time the air travels a distance of 100 feet through the underground loop, it reaches thermal equilibrium with the earth, exiting into the home at a stable pre-cooled temperature of 62 Fahrenheit. During the winter, the process reverses perfectly. Freezing 20 Fahrenheit air enters the same tubes and is warmed up by the earth to 55 Fahrenheit before entering the house, drastically reducing the heating load. To optimize this, modern passive structures utilize high-performance building envelopes with an air tightness rating of less than 0.6 air changes per hour at 50 pascals of pressure, combined with continuous exterior insulation made of high-density mineral wool or wood fiber boards. This ensures that once the earth tubes deliver that passively cooled or warmed air into the living space, the thermal energy cannot escape or infiltrate through the structural shell. The house acts as an unpowered thermodynamic vault, holding its internal temperature steady while the external climate swings wildly. Whether it is an ancient Persian windcatcher drawing cold air from a hidden underground river or a modern earth tube network balancing temperature through soil conductivity, the core lesson is identical. When you design a structure to collaborate with environmental physics rather than fight them with mechanical force, comfort ceases to be an expensive luxury bought from a utility company and becomes a free, natural consequence of intelligent engineering. To truly appreciate the value of a passive thermodynamic system, we have to look at the cold, hard financial reality of how we live today. Let's run the real economics because numbers do not lie. A standard central air conditioning unit for a medium-sized home draws roughly 3,500 watts of electrical power every single hour it runs. If you live in a hot region like Texas, Arizona, or parts of southern Europe, that compressor runs for an average of 10 hours a day during the hottest months. That is 35 kilowatt hours of electricity consumed every single day. At a conservative average utility rate of 16 cents per kilowatt hour, you are spending 5.60 cents a day just to pump heat out of your house. Over a standard 4-month summer cooling season, that totals more than $670. If you live in an area with tiered peak demand pricing or higher base rates, that single appliance can easily drain over $2,200 from your bank account every single year. Over a typical 15-year operational lifespan of an AC unit, you will hand over more than $10,000 to your power company, not including the initial $5,000 to $8,000 cost to purchase and install the mechanical hardware, or the inevitable repair bills when the complex electrical components fail under the stress of summer heat waves. Now, let's look at the financial profile of our passive multi-stage indirect cooler. The initial build cost we established was under $40 for the raw materials. Because it has no compressor, no electric motors, and no high-voltage wiring, its operational electricity consumption is exactly zero. The only ongoing cost is the chemical consumable for the dehumidification core, the calcium chloride salt. In a highly automated or continuous setup, a 50-pound bag of industrial calcium chloride costs around $25. If you do not use a solar thermal regeneration deck, you might go through 2 of these bags a summer, costing you $50. But when you integrate the passive solar thermal regeneration tube we discussed, using the raw 160 Fahrenheit heat of the midday sun to bake the moisture back out of the saturated brine, your salt consumption drops to near zero. You are effectively cycling the exact same chemical battery over and over again for years. The financial comparison is a landslide. You are trading a $15,000 multi-decade mechanical liability for a $40 static device that runs on the sun and pays for itself within the first week of operation. But as engineering educators, we must practice absolute honesty, which means we have to talk about the hard physical limitations of this method. This is not a magic box that works perfectly everywhere, without an asterisk. Every thermodynamic system is bound by its local environmental boundaries. The primary limitation of any adiabatic or evaporative-based cooling system is the ambient wet bulb temperature. The wet bulb temperature is the lowest temperature that can be reached by evaporating water into the air at a constant pressure. If you live in a climate where it is 95 Fahrenheit but the relative humidity is a stifling 90%, the air is already almost entirely saturated with water vapor. The wet bulb temperature under those exact conditions is roughly 92 Fahrenheit. Even with our highly advanced indirect aluminum heat exchanger and a basic salt dryer, a small-scale DIY system will struggle to drop the air temperature significantly below that wet bulb limit without a massive, industrial-sized volume of desiccant salt. If your local climate experiences sustained, high-humidity heat waves where the air never dries out, a pure evaporative system without deep solar regeneration will require frequent manual salt changes to keep the humidity barrier broken. It is a highly localized solution that matches perfectly with arid, semi-arid, or moderately humid regions, but requires significant scaling and advanced multi-stage solar desiccant wheels to operate effectively in tropical, swamp-like environments. Scaling this system up to handle a whole house requires moving away from plastic 5-gallon buckets and into structural integration. To scale the indirect adiabatic engine, you replace the small aluminum foil cube with a dedicated whole-house subfloor or attic heat exchange plenum. This involves using large sheets of corrugated aluminum roofing panels stacked with alternating gaps to create massive cross-flow air channels. You route your home's main fresh air intake through the dry channels of this large matrix, while a solar-powered chimney on the roof or a windcatcher tower drives continuous ambient air through the wet channels, which are kept damp by a low-flow, gravity-fed drip line supplied by a rainwater collection tank. By expanding the surface area of the aluminum plates from a few square inches to 200 square feet, you increase the thermal transfer capacity exponentially, allowing the system to easily cool 2,000 cubic feet of air per minute. You pair this with high-density internal thermal mass, like a central masonry wall or thick stone floors, which acts as a stabilizer, smoothing out any minor temperature fluctuations between day and night. The conclusion of this journey brings us back to how we choose to solve engineering problems. The internet is flooded with viral clips of magic-free energy antennas, hidden patents, and unpowered copper wires promising to run your whole life for $12. Those videos spread because they exploit a desire for an effortless shortcut. But real energy independence, true freedom from the grid, and meaningful reduction of your utility bills don't come from breaking the laws of physics with a secret device. They come from understanding those laws deeply and using them to your advantage. True engineering is unglamorous, it is quiet, and it requires a willingness to look at real numbers and physical constraints. If you want to stop chasing algorithms and start building solutions that actually move the needle on your household expenses, then subscribing to this channel is the simplest way to keep these honest, data-driven breakdowns coming. We don't do conspiracies here. We do physics, we do math, and we build things that work. If you are ready to take your next real step towards self-sufficiency and want to see how we can harvest massive amounts of usable thermal energy right from your backyard without a single commercial solar panel, click on our complete teardown of the high-performance compost water heater right here. Thank you for watching, keep your tools sharp, and I will see you in the next build.